Hello, and welcome. It's good that you're here, settling in, letting the day fall away from your shoulders. Perhaps you're tired, perhaps the hours have been long, or simply full, and now you're looking for something soft to carry you toward rest. That's all right. You don't need to do anything now. You can simply listen, or let the words wash over you like a gentle tide, barely noticing where one thought ends and another begins. Tonight, we're going to explore something that asks almost nothing of us, something that unfolds so slowly that we could watch for a lifetime and barely see it move. We're going to talk about slow chemical reactions, the quiet transformations that happen all around us, beneath us, within us, at a pace so tender and unhurried that they seem to breathe in time with the turning of seasons, the drifting of continents, the patient cycles of the earth itself. If you'd like to join me on other nights like this, you're welcome to follow along. But there's no pressure, no urgency, just rest. Let's begin. The world is always changing, but not always quickly. While some reactions flash and spark in an instant, others take their time, moving through the hours and days and years with the kind of grace that asks us to slow down, to notice, to remember that not everything needs to hurry. These are the reactions that shape mountains, that turn iron into rust, that transform a grape into wine and a forest into coal. They're the alchemists of deep time, working without fanfare, without urgency, simply doing what they do, molecule by molecule, in the vast quietness of chemistry. Consider rust, that soft reddish-brown powder that forms on iron left out in the rain. It is one of the most familiar slow reactions we know. When iron meets oxygen in the presence of water, it begins a transformation so gradual that you might not notice it for days. The iron atoms of the surface start to let go of their electrons, donating them to oxygen. And in this gentle exchange, iron oxide is born. It happens quietly, steadily, without heat or light or sound. Just the patient meeting of metal and air and moisture, day after day, until the surface blooms with that warm, earthy color. Rust is not an enemy, though we sometimes treat it that way. It is simply iron returning to a state closer to the one it held deep in the earth, before we smelted it and shaped it into nails and bridges and tools. In a way, rusting is a kind of homecoming, a slow journey back to oxidation, back to the mineral forms that iron prefers when left to its own quiet devices. It takes weeks, months, sometimes years, depending on the humidity, the temperature, the patience of the air itself. And if you've ever watched a piece of iron rust, you know that it doesn't happen all at once. It begins in small spots, tiny patches where the conditions are just right, where a droplet of water clung a little longer, where the air was a little more generous with its oxygen. From those small beginnings, the rust spreads outward, slowly, softly, like a stain of time itself. It's a reaction that teaches us that transformation doesn't have to be violent or sudden. Sometimes, change is just a whisper, repeated over and over until it becomes visible. The ocean, too, is full of slow chemical reactions, though we rarely think of it that way. When carbon dioxide from the air dissolves into seawater, it forms carbonic acid, a weak acid that very gradually lowers the pH of the ocean. This is a reaction that has been happening for as long as there have been oceans and air, a constant, gentle exchange between sky and sea. The carbon dioxide slips into the water, molecule by molecule, and there it reacts, quietly altering the chemistry of the entire ocean, one tiny shift at a time. This slow acidification has shaped the history of life on Earth. It affects the ability of shellfish and corals to build their calcium carbonate shells and skeletons, because carbonic acid makes it harder for calcium and carbonate ions to come together. It's a reaction that unfolds over decades and centuries, invisible to the naked eye, but profound in its effects. The ocean absorbs, reacts, adjusts, all in its own time, all without hurry. Limestone caves are carved by a reaction so slow that it measures its progress in millennia. Rainwater, slightly acidic from dissolved carbon dioxide, seeps into the ground and meets limestone, which is made of calcium carbonate. The weak acid reacts with the stone, dissolving it, carrying it away, drop by drop, year by year. What remains is a hollow, a cave, a cathedral of stone shaped by the patient persistence of water and chemistry. Inside those caves, the reverse reaction happens just as slowly. When the acidic water drips from the ceiling and meets the air, some of the carbon dioxide escapes, and the calcium carbonate comes out of solution, depositing itself as a tiny crystal. Drip by drip, year by year, stalactites grow downward from the ceiling, stalagmites rise upward from the floor, each one a monument to the slowness of chemistry, each one a testament to the power of repetition over deep time. Some stalactites grow at a rate of less than a millimeter per year. Imagine that. An entire year for a single millimeter, a century for a few centimeters, 1,000 years for the length of your hand. And yet, over tens of thousands of years, these slow accumulations build structures of breathtaking beauty, stone icicles and columns and curtains, all formed by the gentlest of chemical processes, all shaped by patience itself. In your own body, slow reactions are quietly at work too. Collagen, the protein that gives structure to your skin, bones, and connective tissues, undergoes a very gradual process called glycation. Over the years, sugar molecules in your bloodstream slowly attach to collagen fibers, forming what are called advanced glycation end products. This reaction happens so slowly that it's measured over the course of a lifetime, a gentle accumulation that contributes to the natural aging of tissues, the gradual stiffening of skin and blood vessels, the soft passage of time written in chemistry. It's not something to fear, just something to notice, a reminder that our bodies are always in conversation with the molecules around them, always changing, always responding, always moving forward at their own pace. Aging is, in part, a collection of slow chemical reactions, each one contributing a small note to the long, complex symphony of human life. Glass, too, is engaged in a slow transformation, though it happens so gradually that we often think of glass as unchanging. Glass is not a true solid in the way that a crystal is. It's what scientists call an amorphous solid, a material that flows, but so slowly that the flow is almost imperceptible. Over centuries, the molecules in glass very gradually rearrange themselves, responding to gravity, to temperature, to time. Old windows, especially in medieval churches, are sometimes thicker at the bottom than at the top. And while some of this may be due to the way they were made, some of it is the result of this slow, almost glacial flow. The reaction isn't dramatic. It doesn't change the appearance of the glass in a human lifetime. But it's there a quiet reminder that even the things we think of as solid and permanent are, on a long enough time scale, fluid and responsive. Glass is patient. It moves in its own time, unbothered by our brief attention. The formation of soil is another slow chemical ballet, one that takes centuries to complete. When rock is exposed to air and water, it begins to weather. Minerals react with oxygen, with carbon dioxide, with the weak acids produced by lichens and plant roots. Feldspars break down into clays. Iron oxidizes. Silicates dissolve. Bit by bit, the rock crumbles, its minerals transformed into new compounds, its structure softened and loosened. This weathering is not fast. A single centimeter of soil can take hundreds of years to form, depending on the climate, the type of rock, the presence of life. In cold, dry places, the process is even slower. In warm, wet places, it moves a little faster, but still, it is measured in human lifetimes, in generations, in the long, slow breath of geology. Soil is a gift of time, a product of patience, a reminder that the ground beneath our feet is not static, but slowly, constantly renewing itself. Fossilization, too, is a slow chemical process, one that turns bone and wood into stone over millions of years. When an organism dies and is buried quickly, before it can decay completely, minerals in the surrounding water begin to seep into the pores and cavities of the tissue. Over time, these minerals, often silica or calcium carbonate, replace the original organic material, molecule by molecule, preserving the shape and structure in stone. It's a transformation that requires the right conditions: burial, the presence of mineral-rich water, the absence of oxygen, and above all, time. Millions of years, usually, for the process to complete. The result is a fossil, a stone echo of a life that once was a record written in chemistry, preserved by the slow, steady replacement of one kind of matter with another. Petrified wood is a beautiful example of this. Trees that fell into rivers or volcanic ash millions of years ago, buried before they could rot, slowly had their cellulose and lignin replaced by minerals. The wood turned to stone, but the grain, the rings, the texture of the original tree remained, captured in silica, a memory held in stone. It's a process so slow that it spans geological epochs, so thorough that the final product is no longer wood at all, but a perfect mineral replica, heavy and hard and patient. Coal formation is another slow reaction, one that transforms plant matter into rock over tens of millions of years. When plants die in swampy, oxygen-poor environments, they don't fully decay. Instead, they accumulate in thick layers of peat, compressed by the weight of sediment above them. Over time, heat and pressure drive out water, oxygen, and hydrogen, leaving behind an ever more concentrated form of carbon. First comes peat, then lignite, then bituminous coal, and finally, if the conditions are right and the time is long enough, anthracite, a hard, shiny, almost pure form of carbon. The entire process can take 50 million years or more, a slow distillation of ancient sunlight, a chemical journey from leaf to stone, from forest to fuel, all happening in the deep, quiet darkness beneath the earth. When you hold a piece of coal, you're holding time itself, compressed and transformed, the chemical memory of forests that grew and died long before humans walked the earth. It's a slow reaction made solid, a testament to the power of pressure and time and chemistry working together across unimaginable spans of years. Tarnish on silver is another slow reaction, one that happens when silver reacts with sulfur compounds in the air. The sulfur comes from many sources, from the breakdown of proteins, from volcanic gases, from pollution, from the rubber and carpet padding. When sulfur meets silver, they react to form silver sulfide, a dark, tarnished layer that dulls the bright shine of the metal. It's a slow process, usually taking weeks or months to become noticeable, depending on the environment. In a clean, dry place, silver might stay bright for years. In a humid, sulfur-rich environment, it tarnishes more quickly. But even at its fastest, it's a reaction that unfolds gradually, quietly, without drama. The silver doesn't corrode or crumble. It simply darkens, its surface transformed by the gentle chemistry of time and air. And like rust, tarnish is not destruction. It's transformation. The silver is still there, just wearing a different face, a darker patina that some people find beautiful, a sign of age and use in history. Tarnish can be polished away, of course, but it always returns, patient and persistent, a reminder that silver, like all metals, is in constant, slow conversation with the world around it. The aging of wine is a slow chemical process that transforms sharp, young flavors into something complex and smooth. After the initial fermentation, when yeast has turned sugar into alcohol, the wine continues to change. Tannins from grape skins and seeds slowly polymerize, forming longer chains that feel softer on the tongue. Acids mellow, esters form, contributing new aromas. Oxygen seeps in through the cork, very slowly, driving gentle oxidation reactions that add depth and character. This aging can take years, even decades, depending on the wine. It's a process that cannot be rushed. The reactions need time to unfold, to interact, to balance each other. A wine that is harsh and tannic in its youth becomes, with patience, something graceful and harmonious. Its chemistry as art, transformation as meditation, a reminder that some of the best things in life require us to wait, to trust, to let time do its quiet work. Cheese, too, ages through slow chemical reactions. After the milk has been curdled and the curds have been pressed and salted, enzymes and bacteria continue to work, breaking down proteins and fats into smaller, more flavorful molecules. A young cheddar is mild and smooth. An aged cheddar, after months or years, develops sharp, complex flavors and a crumbly texture, all because of the slow, steady work of enzymes cleaving peptide bonds, lipases releasing fatty acids, and bacteria producing a symphony of aromatic compounds. The process is so slow that cheesemakers measure it in months and years. Some cheeses are aged for a decade or more, developing flavors so intense and intricate that they seem to contain entire landscapes. Grass, earth, time, patience. It's a transformation you can taste, a slow reaction made delicious, a reminder that complexity often comes from waiting, from allowing chemistry to unfold at its own pace. The patina on copper and bronze is another slow reaction, one that gives old statues and roofs their distinctive green color. When copper is exposed to air and moisture, it slowly oxidizes, first forming a brown layer of copper oxide, then over years or decades, reacting further with carbon dioxide and sulfur compounds to form copper carbonate and copper sulfate. The green or blue-green patina we associate with aged copper. The Statue of Liberty, for example, was originally a shiny reddish-brown. Over the course of about 30 years, it slowly turned green as the copper skin reacted with the salty, humid air of New York Harbor. The patina is not damage. It's a protective layer, actually slowing further corrosion, preserving the metal beneath. It's a slow reaction that transforms appearance while protecting substance, a chemical process that adds beauty and history to the metal it touches. In ancient bronze statues, the patina can be centuries old, a chemical record of the air and water and time the statue has experienced. Archaeologists and conservators can sometimes read this patina like a book, learning about the environment the statue lived in, the care it received, the slow chemistry of its aging. It's a layer of time made visible, a gentle transformation that connects the past to the present. The formation of petroleum is one of the slowest chemical processes we know, taking millions of years to transform microscopic marine organisms into crude oil. When plankton and algae die, they sink to the ocean floor, accumulating in sediments. If the conditions are right, if there's little oxygen, if the sediments are buried deeply enough, the organic matter is slowly transformed by heat and pressure. First, it becomes a waxy substance called kerogen. Then, as the temperature rises with deeper burial, the kerogen breaks down into hydrocarbons, oil, and natural gas. The process typically takes between 10 and 100 million years, depending on the temperature and pressure. It's a slow distillation of ancient life, a chemical journey from organism to energy, from seed to stone to liquid fuel. When we pump oil from the ground, we're extracting the product of one of the slowest reactions on Earth, a substance that took longer to form than our entire species has existed. It's a humbling thought, a reminder of the deep time scales on which some chemical processes operate, the vast patience of the Earth itself. The weathering of granite is another slow reaction, one that gradually breaks down one of the hardest rocks on Earth. Granite is made of minerals like quartz, feldspar, and mica, and when it's exposed to air and water, those minerals begin to react. Feldspar, in particular, slowly reacts with carbonic acid and rainwater, breaking down into clay minerals and releasing ions like potassium and sodium into the water. This process is so slow that a granite mountain can stand for millions of years, barely changing. But over geological time, even granite yields, crumbling grain by grain, its minerals transformed, its structure softened. The clay washes away, the quartz grains are freed, and what was once a solid mountain becomes, eventually, sediment, soil, sand on a distant beach. It's a slow dissolution, a patient unmaking, a reminder that even the hardest things are not permanent, just slow to change. The formation of clay itself is a slow chemical reaction, a transformation of rock into something soft and pliable. When minerals like feldspar weather, they break down into clay minerals, kaolinite, montmorillonite, illite. These are new compounds with different structures, different properties, formed by the slow rearrangement of silicon, aluminum, and oxygen atoms in the presence of water. Clay is not just ground-up rock. It's chemically transformed rock, the product of slow reactions between minerals and water, often taking thousands of years to form. When you hold clay in your hands, you're holding the result of deep time and patient chemistry, a substance that began as stone and became, through slow transformation, something that can be shaped, that holds water, that can be fired into pottery. It's a gift of slow reactions, a material made possible by the unhurried work of weathering. The carbonation of concrete is a slow reaction that actually strengthens the material over time. Concrete is made from cement, which contains calcium hydroxide. When exposed to air, the calcium hydroxide slowly reacts with carbon dioxide, forming calcium carbonate. This reaction progresses inward from the surface, very gradually, over years and decades. The carbonation makes the concrete denser and harder, improving its strength. It's one reason why old concrete structures can be so durable. They've been slowly strengthening themselves, reacting with the air, transforming chemically as they age. It's a slow process, usually penetrating only a few millimeters per year, but over the lifetime of a building, it can make a significant difference, a quiet chemical reinforcement happening invisibly within the walls. However, carbonation also lowers the pH of the concrete, which can eventually affect the steel reinforcement inside. So, it's a double-edged process, strengthening the concrete itself while potentially making conditions less protective for the metal within. It's a reminder that slow reactions can have complex effects, beneficial in some ways, challenging in others, all unfolding at their own patient pace. The formation of desert varnish is one of the most mysterious slow reactions in nature. Desert varnish is a thin, dark coating that forms on rocks in arid environments, giving them a shiny, almost lacquered appearance. It's made mostly of manganese and iron oxides, but the exact process by which it forms is still not fully understood. It seems to involve a combination of chemical weathering, the activity of bacteria, and the slow accumulation of wind-blown dust. Microbes may help to concentrate the manganese and iron, oxidizing them and depositing them on a rock surface. The process is incredibly slow. Desert varnish can take thousands of years to form a coating just a fraction of a millimeter thick. Some desert varnish is so old that it contains a record of past climates, a chemical archive of the air and water and life that touched the rock over millennia. Ancient peoples sometimes carve through the varnish to create petroglyphs, exposing the lighter rock beneath, creating images that have lasted for thousands of years, preserved by the slow chemistry of the desert itself. The breakdown of plastics is a slow reaction that we're only beginning to understand. Most plastics are polymers, long chains of repeating molecules, and they're designed to be stable, to resist breaking down. But over time, exposure to sunlight, oxygen, and microbes can slowly degrade them. Ultraviolet light from the sun breaks chemical bonds in the polymer chains, making them shorter and weaker. Oxygen reacts with the fragments, creating new functional groups. The plastic becomes brittle, discolored, cracked. Eventually, it breaks into smaller and smaller pieces, but the polymer molecules themselves can persist for decades, even centuries, slowly breaking down, slowly reacting, but never quite disappearing. Some bacteria and fungi have evolved enzymes that can break down certain plastics, but the process is still very slow, much slower than the breakdown of natural materials like wood or paper. It's a reminder that the materials we create can outlast us by generations, slowly reacting with the environment, slowly transforming, but on timescales that challenge our ability to imagine or manage them. The formation of opal is a slow chemical process that creates one of the most beautiful gemstones on Earth. Opal forms when silica-rich water seeps into cracks and cavities in rock. As the water evaporates, it leaves behind tiny spheres of silica, which slowly settle and pack together in order to raise. Over thousands or millions of years, these silica spheres build up, layer by layer, forming opal. The regular arrangement of the spheres diffracts light, creating the flashes of color, red, green, blue, that make opal so prized. It's a slow crystallization, a patient accumulation, a gemstone formed by the gentle evaporation of water and the quiet settling of silica, one microscopic sphere at a time. The process requires stability. The conditions have to remain just right for long enough for the opal to form. Too much disturbance, and the spheres don't pack properly. Too little silica, and the opal doesn't grow. It's a delicate, slow reaction, one that produces something rare and beautiful, a stone that seems to hold light itself, captured by the patient work of chemistry over deep time. The slow oxidation of fats is a reaction that happens in stored food, causing what we call rancidity. When fats are exposed to oxygen, they slowly react, forming peroxides and aldehydes that have unpleasant smells and flavors. The reaction is accelerated by light and heat, but even in cool, dark conditions, it happens, just more slowly. This is why oils and nuts and fatty foods eventually go bad, even if they're sealed and stored carefully. The oxygen in the air, or even the tiny amount of oxygen dissolved in the oil itself, slowly reacts with the unsaturated fats, breaking them down, transforming them into compounds that taste and smell off. It's a slow reaction, usually taking months, but inevitable, a reminder that even preserved food is not static, but slowly changing, slowly reacting, slowly moving toward a different chemical state. Antioxidants, like vitamin E, can slow this reaction by reacting with the peroxides before they can damage the fats. It's a chemical defense, a way of intercepting the slow oxidation, buying time, preserving freshness a little longer. But even with antioxidants, the reaction continues, just more slowly, a patient chemical process that eventually catches up. The slow hydrolysis of esters is a reaction that happens in everything from stored wine to old perfumes. Esters are compounds that often have fruity or floral smells, and they're formed by the reaction of an alcohol with an acid. But in the presence of water, the reaction can slowly reverse. The ester breaks down, releasing the alcohol and acid again. This is why old wine can develop off flavors, why old perfumes can smell different from when they were new. The esters that gave them their characteristic aromas are slowly hydrolyzing, slowly breaking apart, transforming the scent profile over months or years. It's a gentle chemical drift, a slow change in the balance of molecules, a reminder that even smells are not permanent, but the result of dynamic, slowly shifting chemistry. The formation of kidney stones is a slow chemical process that happens when minerals in urine gradually crystallize. Calcium oxalate, calcium phosphate, or uric acid can slowly come out of solution, forming tiny crystals that, over weeks or months, can grow into stones. The process is influenced by the concentration of minerals, the pH of the urine, the presence of substances that promote or inhibit crystal growth. It's a slow precipitation, a gradual accumulation, a chemical process that usually takes time to become a problem. The body has mechanisms to prevent this, proteins and citrate that inhibit crystal formation, but sometimes the balance tips and the slow reaction proceeds, building stones one crystal at a time. It's a reminder that our bodies are full of chemistry, constantly balancing reactions, constantly managing the slow processes that could, if left unchecked, cause problems. Most of the time, the balance holds, the slow reactions are kept in check, and we remain healthy, unaware of the quiet chemical management happening inside us every day. The tanning of leather is a slow chemical process that transforms raw animal hide into a durable, flexible material. Traditional vegetable tanning uses tannins, compounds found in tree bark, leaves, and nuts, which slowly bind to the collagen proteins in the hide, cross-linking them, making them resistant to decay and water. The process can take weeks or even months as the hides soak in progressively stronger tannin solutions, allowing the molecules to slowly penetrate and react with the collagen. It's a patient transformation, a slow chemical binding that turns something perishable into something that can last for decades or centuries. The leather darkens, stiffens, develops character, all through the slow work of tannins and time. Modern chrome tanning is faster, but traditional vegetable tanning is still prized for the quality and durability it produces, a testament to the value of slow chemical processes, of allowing reactions to unfold at their own pace, of trusting time to do the work that haste cannot. The slow decomposition of cellulose in landfills is a reaction that can take decades. Cellulose, the main component of plant cell walls, is a polymer of glucose, and it can be broken down by bacteria and fungi. But in the oxygen-poor environment of a landfill, the process is very slow. Newspapers buried in landfills have been found still readable after 30 or 40 years, barely decomposed, because the conditions weren't right for the slow chemical and biological breakdown of cellulose. In the presence of oxygen, with the right microbes, cellulose breaks down much faster, but buried deep in compacted waste, it persists a slow reaction waiting for the conditions it needs to proceed. It's a reminder that decomposition is not automatic or instantaneous. It's a chemical process that depends on the environment, on the presence of the right organisms, on oxygen and moisture and time. Even something as biodegradable as paper can last for decades if the conditions for its slow breakdown are not met. The aging of whiskey in barrels is a slow chemical process that transforms harsh, clear spirit into something smooth and complex. The whiskey slowly reacts with compounds in the wood. Lignins break down into vanillin, giving vanilla notes. Tannins contribute astringency and color. Lactones add coconut and woody flavors. Oxygen seeps in through the wood, very slowly, driving gentle oxidation reactions. The whiskey expands and contracts with temperature changes, moving in and out of the wood, extracting more compounds, allowing more reactions. The process takes years, often a decade or more, for the full transformation to occur. It's a slow maturation, a patient dialogue between liquid and wood, a chemical conversation that cannot be rushed. Distillers know that time is an ingredient, that the slow reactions happening in the barrel are what turn raw spirit into something worth savoring. Its chemistry is craft, transformation is tradition, a reminder that some of the best things require us to wait, to trust the slow work of time and wood and patience. The transformation of starch within your body unfolds in a slow cascade that begins even before you swallow. Amylase enzymes in your saliva start breaking down complex carbohydrates into simpler sugars, a process so gradual that a piece of bread held in your mouth for several minutes will begin to taste subtly sweeter. This is chemistry at a human pace, gentle enough that you can sense it happening, molecule by molecule, as long chains of glucose units are snipped into smaller fragments. The reaction continues in your digestive system for hours, a quiet river of molecular change that feeds you without fanfare or haste. Deep within the Earth's crust, the metamorphosis of limestone into marble proceeds across millions of years. Heat and pressure rearrange the calcium carbonate crystals, transforming the sedimentary rock grain by grain into something denser, more lustrous, more enduring. The chemical bonds shift and realign in response to conditions that would seem extreme to us, but are merely steady and patient to the planet. No sudden flash marks this change, only the accumulation of countless small adjustments, each crystal finding a new geometry, each layer compressing into the next. When we quarry marble and admire its beauty, we are looking at the result of chemistry that moves slower than continental drift, quieter than the growth of mountains. The browning of an apple slice left on a countertop is a slow oxidation, a meeting between the fruit's phenolic compounds and oxygen in the air. Enzymes called polyphenol oxidases facilitate this reaction, which would happen even without them, but much more slowly still. The flesh darkens over the course of minutes to hours, depending on the variety of apple and the temperature of the room. This is the same family of reactions that turns tea dark when it steeps, that gives color to chocolate during fermentation, that deepens the hue of a bruise on your skin. It is chemistry visible to the naked eye, unfolding at a pace that invites observation, a gentle reminder that change does not always announce itself with violence. In the deep ocean, calcium carbonate from the shells of tiny organisms drifts downward through the water column, dissolving slowly as it sinks. The deeper the water, the colder and more acidic it becomes, and the more readily the carbonate dissolves. This is the carbonate compensation depth, a boundary below which shells cannot survive intact. The reaction between calcium carbonate and carbonic acid in seawater is slow and steady, a molecular negotiation that has been taking place for hundreds of millions of years. It regulates the ocean's chemistry, buffers changes in acidity, and shapes the very floor of the sea. The slowness of this dissolution is part of what keeps our planet's carbon cycle stable, a quiet thermostat operating in the abyss. The yellowing of old paper is a slow oxidation of the lignin and cellulose fibers within it. Lignin, a complex polymer that gives wood its rigidity, breaks down in the presence of light and oxygen, forming chromophores, molecules that absorb blue light and reflect yellow and brown. This is why newspapers turn brittle and sepia-toned, why old books smell faintly of vanilla as the lignin degrades into vanillin. The reaction accelerates in sunlight, but continues even in darkness. a gradual surrender to entropy that can take decades or centuries, depending on the paper's composition. Archivists slow this process with controlled environments, cool and dry and dark, but they cannot stop it entirely. The chemistry of aging is patient and inexorable. Concrete continues to harden long after it is poured, a process called curing that can extend for years. The calcium silicate hydrates that form when cement reacts with water grow and interlock, filling microscopic voids and increasing the material's strength. Even after a building has been occupied for decades, the concrete in its foundation is still slowly reacting, still gaining compressive strength, still binding itself more tightly together. This is one reason ancient Roman concrete, made with volcanic ash and seawater, has endured so remarkably well. It contains minerals that continue to crystallize and heal cracks over centuries. The slowness of a reaction is a gift, a form of self-repair built into the material's chemistry. The formation of natural gas from organic matter buried in sediment is a process measured in millions of years. As layers of mud and sand accumulate above ancient swamps and shallow seas, the pressure and temperature gradually increase. Bacteria first break down the organic material into simpler compounds, and then, as conditions become too hot for life, purely chemical reactions take over. Long-chain hydrocarbons are cracked into shorter ones, releasing methane and other light gases. This thermogenic process happens so slowly that the gas we extract today was formed from organisms that lived when dinosaurs walked the earth. It is fossil sunlight, captured by ancient photosynthesis and transformed by the planet's patient heat. The slow reaction between carbon dioxide and the minerals in basalt rock offers a glimpse of how we might store excess carbon from the atmosphere. When CO2 is dissolved in water and injected into basaltic formations, it reacts with calcium, magnesium, and iron in the rock to form stable carbonate minerals. In nature, this weathering process takes thousands of years, but in the controlled environment of a geological storage site, it can happen in a matter of months to years, still slow by human standards, but fast enough to be useful. The reaction is exothermic, releasing a little warmth as the carbon is locked away in solid form, a gentle heat that signals the transformation from gas to stone. The darkening of silver jewelry into tarnish is a reaction with hydrogen sulfide, a compound present in trace amounts in the air, especially in areas with volcanic activity or industrial pollution. Silver sulfide forms on the surface of the metal, a thin layer that starts as a golden hue and deepens through purple and blue into black. The reaction is slow under normal conditions, taking weeks or months to become noticeable, but it can be accelerated by contact with sulfur-containing foods like eggs or by the sulfur compounds in human sweat. Polishing removes the tarnish, but the silver itself is slightly diminished each time, molecule by molecule, a slow erosion that is the price of beauty. The conversion of nitrites to nitrates in cured meats is a slow process that contributes to both preservation and flavor. Nitrites, added to prevent the growth of Clostridium botulinum, gradually oxidize into nitrates over weeks and months. This reaction is influenced by the presence of oxygen, the acidity of the meat, and the temperature at which it is stored. The chemistry is delicate, a balance between safety and taste, and it unfolds slowly enough that traditional curing methods rely on time as much as on any single ingredient. The pink color of cured ham, the tangy depth of salami, the complex aroma of aged sausage, all are the products of reactions that cannot be hurried without loss. The slow polymerization of linseed oil as it dries has been used by artists for centuries. When exposed to air, the unsaturated fatty acids in the oil react with oxygen, forming crosslinks that gradually transform the liquid into a solid film. This process, called oxidative polymerization, can take days to weeks for the surface to dry to the touch and months to years for the paint to fully cure. The slow drying allows pigments to blend and settle, gives the artist time to work, and contributes to the luminous quality of oil paintings. Even in museums, paintings that are centuries old are still slowly curing, their chemistry still active, still evolving in the quiet darkness between exhibitions. The formation of peat from moss and other plant material in waterlogged bogs is a slow accumulation that can eventually lead to coal. In the acidic, oxygen-poor environment of a peat bog, decomposition is greatly slowed. Bacteria and fungi that would normally break down plant matter cannot thrive, and so the dead vegetation compresses and transforms, layer upon layer, at a rate of about a millimeter per year. Over thousands of years, peat deposits can grow meters thick. If buried deeply enough and subjected to heat and pressure, this peat will eventually become lignite, then bituminous coal, then anthracite, a transformation that takes millions of years and is one of the slowest chemical journeys on Earth. The slow reaction between aluminum and oxygen creates a protective layer of aluminum oxide on the metal surface, a process called passivation. This oxide layer, only a few nanometers thick, forms within minutes of exposure to air and then grows more slowly over time. It is hard, transparent, and chemically stable, shielding the underlying aluminum from further corrosion. This is why aluminum, despite being a reactive metal, can be used in construction, cookware, and aircraft without rusting away. The slowness of the oxidation beyond that initial layer is what makes aluminum practical, a quiet truce between metal and atmosphere that has enabled much of modern engineering. The gradual leaching of minerals from soil by rainwater is a slow process that shapes landscapes and determines which plants can grow where. Water, slightly acidified by dissolved carbon dioxide, percolates through the soil, dissolving calcium, magnesium, potassium, and other nutrients. Over decades and centuries, this leaching can deplete the topsoil, leaving it acidic and infertile, or it can carry minerals downward to form distinct soil horizons. In tropical regions with heavy rainfall, the process is faster, but even there it unfolds over generations. In temperate zones, the slow migration of minerals through soil is measured in centuries, a quiet redistribution of the Earth's chemical wealth. The transformation of cholesterol into vitamin D in your skin when exposed to sunlight is a photochemical reaction that happens in minutes, but is part of a slower metabolic cascade. UVB radiation converts 7-dehydrocholesterol into pre-vitamin D3, which then slowly isomerizes into vitamin D3 over the course of hours, driven by body heat alone. This vitamin is then transported to the liver and kidneys, where it undergoes further slow hydroxylation reactions over days to become the active hormone calcitriol. The entire process, from sunlight to functional vitamin, is a gentle sequence of chemical steps, each one taking its time, each one essential to bone health, immune function, and cellular regulation. The slow carbonation of concrete exposed to air is a process that gradually changes the material's chemistry and can affect its ability to protect embedded steel. Carbon dioxide from the atmosphere diffuses into the concrete and reacts with calcium hydroxide to form calcium carbonate. This reaction slowly lowers the pH of the concrete, a process that can take decades to penetrate more than a few centimeters. As long as the concrete remains alkaline, the steel reinforcement inside is protected from corrosion by a passive oxide layer. But once carbonation reaches the steel, that protection is lost and rusting can begin. The slowness of carbonation is a race against time in the life of a structure, a chemical clock ticking imperceptibly within the walls. The aging of balsamic vinegar in wooden casks is a slow concentration and transformation that can span decades. As water evaporates through the porous wood, the vinegar thickens and its flavors deepen. Slow oxidation reactions, catalyzed by trace metals and influenced by the wood's tannins, create new aromatic compounds. Esters form and break down. Acids mellow. Sugars caramelize slightly in the warmth of the aging room. Traditional balsamic vinegar is moved through a series of casks of decreasing size, each made from a different wood: oak, chestnut, cherry, juniper, each contributing its own subtle chemistry. The result is a liquid that is the product of patient, unhurried transformation, a collaboration between grape, wood, air, and time. The slow dissolution of kidney stones by medical treatment is a chemical process that requires patience and persistence. Stones made of uric acid can be gradually dissolved by alkalinizing the urine, which increases the solubility of uric acid and allows it to slowly wash away. The process can take weeks to months, depending on the size of the stone and the consistency of treatment. It is a gentle alternative to more invasive procedures, a chemical negotiation between medicine and mineral, a slow reversal of the crystallization that caused the problem in the first place. The body becomes its own slow laboratory, adjusting pH, managing concentration, dissolving what it once mistakenly built. The formation of clay minerals from the weathering of feldspar is one of the slowest and most important reactions in the rock cycle. Feldspar, a common mineral in granite and other igneous rocks, reacts with water and carbonic acid over thousands to millions of years, breaking down into clay minerals like kaolinite. This transformation involves the slow hydrolysis of aluminum silicate structures, the leaching away of potassium and sodium, and the rearrangement of atoms into new crystal lattices. The resulting clay is soft, fine-grained, and chemically different from its parent rock. It is the material of pottery, of fertile soil, of river deltas, and it represents one of the fundamental ways that mountains are slowly dismantled and redistributed across the Earth's surface. The slow hydrolysis of esters and stored cooking oils is what leads to rancidity over time. Triglycerides, the main component of fats and oils, can react with water to break down into free fatty acids and glycerol. This reaction is accelerated by heat, light, and the presence of certain enzymes or metals. But even under ideal storage conditions, it proceeds slowly and inevitably. The free fatty acids have a sharp, unpleasant taste and smell, signaling that the oil is no longer at its best. Antioxidants can slow the process by intercepting the free radicals that drive oxidation, but they cannot stop hydrolysis entirely. The chemistry of spoilage is a reminder that even the most stable substances are slowly changing, slowly surrendering to entropy. The slow reaction between lime mortar and carbon dioxide in the air is what allows traditional masonry to harden over months and years. Lime mortar, made from calcium hydroxide, absorbs CO2 and converts back into calcium carbonate, the same mineral from which the lime was originally made by heating limestone. This carbonation process is slow because it depends on the diffusion of carbon dioxide through the mortar, which is hindered by moisture and the density of the material. A thick wall of lime mortar may take years to fully carbonate at its core, and during that time it remains somewhat soft and workable. This slow setting is part of what makes lime mortar flexible and breathable, qualities that have allowed historic buildings to endure for centuries without cracking. The gradual breakdown of nylon and other synthetic polymers in the environment is a slow process that scientists are still working to understand. Nylon is resistant to most forms of chemical degradation, but over decades it can slowly hydrolyze, especially in the presence of moisture and heat. The amide bonds that link the monomers together are susceptible to attack by water molecules, a reaction that is extremely slow at room temperature but accelerates in hot, humid conditions. This is why old nylon rope becomes brittle, why vintage stockings develop runs more easily, why the plastic components of aging equipment begin to fail. The slowness of this degradation is both a blessing and a curse. It makes nylon durable, but it also means that discarded nylon persists in the environment for many human lifetimes. The slow formation of secondary minerals in the cavities of volcanic rocks creates the beautiful specimens prized by collectors. After lava cools and solidifies, gas bubbles and voids remain within the rock. Over thousands to millions of years, groundwater percolates through these spaces, carrying dissolved silica, calcium, iron, and other elements. These minerals slowly precipitate out of solution, layer by layer, forming agates, zeolites, calcite crystals, and other secondary minerals. The banding in agates records subtle changes in the chemistry of the groundwater over time. Each layer is a snapshot of ancient conditions. The process is so slow that a single agate nodule may represent tens of thousands of years of patient deposition. A geological painting created one molecular layer at a time. The slow oxidation of iron within your body is carefully controlled by proteins that prevent harmful reactions. Iron is essential for carrying oxygen in your blood, but free iron can catalyze the formation of reactive oxygen species that damage cells. Your body sequesters iron in proteins like ferritin and transferrin, releasing it only when needed and always under strict regulation. Even so, iron slowly oxidizes from the ferrous to the ferric state, and enzymes must constantly work to reduce it back again. This careful management of iron chemistry is a slow, continuous process, a balancing act that has been refined over billions of years of evolution. The slowness of controlled oxidation is what allows life to harness iron's reactivity without being destroyed by it. The gradual saponification of fats in ancient shipwrecks creates a waxy substance called adipose sear, or corpse wax. In the oxygen-poor, alkaline environment of certain underwater sites, the triglycerides in human or animal remains react with minerals in the sediment to form a mixture of fatty acid salts, essentially soap. This transformation can take months to years and preserves the shape of soft tissues long after they would otherwise have decomposed. Adipose sear is chemically stable and can persist for centuries, providing forensic scientists and archaeologists with information that would otherwise be lost. It is a slow, spontaneous embalming, a chemical accident that turns decay into preservation. The slow reaction between ozone and rubber causes tires and seals to crack and degrade over time. Ozone, present in small amounts in the atmosphere and generated by electrical equipment, attacks the double bonds in rubber polymers, breaking the chains and forming brittle, oxidized fragments. This reaction is slow under normal conditions, but is accelerated by stretching, heat, and UV light. Antioxidants are added to rubber compounds to absorb the ozone or to heal the broken bonds, but they are gradually consumed, and eventually the protection fails. The fine cracks that appear on the sidewalls of old tires are the visible result of this slow chemical attack, a reminder that even materials designed for durability are engaged in a constant, losing battle with the atmosphere. The slow conversion of graphite into diamond, though thermodynamically favorable at high pressure, is kinetically hindered and requires geological timescales. Deep within the Earth's mantle, where pressures exceed 50,000 atmospheres and temperatures reach over 1,000 degrees Celsius, carbon atoms in graphite are slowly rearranged into the denser, tetrahedral structure of diamond. The activation energy for this transformation is so high that even under these extreme conditions, the process takes millions of years. Diamonds brought to the surface by volcanic eruptions are therefore ancient, often billions of years old, each one a testament to the slowness of solid-state chemistry under the crushing weight of the planet. The gradual yellowing of plastics exposed to sunlight is a result of slow photodegradation. UV radiation breaks chemical bonds in the polymer chains, creating free radicals that react with oxygen to form chromophoric groups, molecular structures that absorb visible light and impart color. This process is slow, taking months to years depending on the intensity of the light and the type of plastic, but it is relentless. White plastics turn yellow, clear plastics become cloudy, and the material becomes brittle as the polymer chains shorten. UV stabilizers can slow this degradation by absorbing the harmful radiation or by quenching the free radicals, but they are gradually depleted, and the slow march toward discoloration and failure continues. The formation of natural mummies in dry, stable environments is a slow desiccation and chemical stabilization. In the absence of moisture, the bacteria and enzymes that normally decompose tissue cannot function effectively. Water slowly evaporates from the body, and the remaining tissues undergo slow oxidation and cross-linking reactions that harden and preserve them. This process can take months to years, depending on the environment, and the result is a body that can remain intact for millennia. The mummies of the Atacama Desert, the Darien Basin, and the high Andes are all products of this slow, natural preservation, a chemical quietude that halts decay and suspends time. The slow reaction between hydrogen and oxygen in a fuel cell generates electricity with water as the only byproduct. Though this reaction can be explosive when uncontrolled, in a fuel cell, it is mediated by catalysts and occurs at a measured, steady pace. Hydrogen molecules are split into protons and electrons at the anode. The electrons flow through an external circuit, doing useful work, while the protons migrate through a membrane to the cathode, where they combine with oxygen and the returning electrons to form water. The reaction is clean, efficient, and as fast or as slow as the demand for electricity requires. It is chemistry harnessed for power, a slow burn that produces no flame, only a gentle warmth and a trickle of pure water. The aging of whiskey in charred oak barrels is a slow extraction and transformation of flavors over years or even decades. The alcohol slowly dissolves lignin, tannins, and other compounds from the wood, while also undergoing slow oxidation and esterification reactions. Temperature fluctuations cause the liquid to expand into the wood and contract back out, enhancing the extraction. Volatile compounds evaporate through the barrel, a loss known as the angel's share, which slowly concentrates the remaining flavors. The result is a spirit of extraordinary complexity, each bottle a liquid record of slow chemistry, patient craftsmanship, and the passage of time. The journey through slow chemistry continues with the quiet persistence of natural processes unfolding across time. Each reaction carries its own rhythm, its own patient transformation that asks nothing of us but observation and wonder. Consider the way that copper roofs age across centuries, shifting through a spectrum of colors that architects and artists have learned to anticipate. When copper first meets the air, it gleams with that warm reddish-orange glow we recognize instantly. But oxygen begins its work immediately, forming a thin layer of copper oxide that darkens the surface to brown within weeks or months. This is only the beginning. Over years, this brown layer continues to react with moisture, carbon dioxide, and sulfur compounds in the atmosphere, gradually building a protective layer of copper carbonate and copper sulfate. The final result is that beloved blue-green patina, verdigris, which can take 20 to 30 years to fully develop in temperate climates. The Statue of Liberty wears this patient transformation as her skin, a chemical process that began the moment her copper sheets were exposed to New York's harbor air. The patina is not decay, but protection, a shield that forms so slowly that it outlasts generations, preserving the metal beneath for centuries to come. And in the depths of old-growth forests, fallen trees undergo a transformation so gradual that entire ecosystems depend upon its slowness. When a massive trunk collapses to the forest floor, it becomes what ecologists call a nurse log, and its decomposition is a chemical symphony played across decades. Fungi begin the work, secreting enzymes that break down lignin and cellulose, the structural polymers that gave the tree its strength. These are hydrolysis reactions, water molecules slowly cleaving the long chains into smaller sugars and phenolic compounds. Bacteria join the process, oxidizing some compounds while reducing others in the oxygen-poor interior of the log. The wood softens year by year, its density decreasing as carbon dioxide and water are released. Seedlings take root in the spongy surface, drawing nutrients from the slow chemical dissolution of what was once a living giant. A large conifer log in a temperate rainforest may take 50 to 200 years to fully decompose, depending on its size and species. The chemistry never rushes, and the forest has learned to depend upon this patience, timing its cycles of renewal to match the steady pace of decay. In the human body, bones are constantly remodeling themselves through a slow chemical dialogue between construction and dissolution. Cells called osteoclasts secrete acids and enzymes that gradually dissolve small portions of bone mineral, primarily hydroxyapatite, a calcium phosphate compound. This is a controlled acidic dissolution, releasing calcium and phosphate ions into the bloodstream. Meanwhile, osteoblasts build new bone matrix, depositing collagen and facilitating the slow precipitation of new hydroxyapatite crystals. The entire skeleton is replaced approximately every 10 years through this patient process, though some bones renew faster than others. The chemistry operates at a pace that maintains strength while allowing adaptation to changing mechanical stresses. When you rest at night, these reactions continue in the darkness of your body, quietly reshaping the framework that carries you through the world. There is something deeply restful in knowing that your very structure is being gently renewed, atom by atom, through chemical reactions that require no conscious effort, no attention, only time. The formation of natural pearls in oysters and mussels is another marvel of slow chemistry, a defensive response that becomes beauty through patient repetition. When an irritant, perhaps a grain of sand or a parasite, lodges in the soft tissue of a mollusk, the animal begins coating it with nacre, also called mother of pearl. Nacre is composed of aragonite, a crystalline form of calcium carbonate, bound together with proteins and polysaccharides secreted by the mollusk's mantle tissue. Each layer is incredibly thin, only a few micrometers, and the mollusk adds them slowly, one atop another, in a process that can take several years to produce a pearl of significant size. The aragonite crystals are arranged in flat plates with organic matrix between them, creating a structure that diffracts light into iridescent colors. The chemical precipitation of calcium carbonate from the mollusk's body fluids is carefully controlled, maintaining precise pH and ion concentrations. A natural pearl might grow at a rate of only a few millimeters per year, and the finest pearls may take 5 to 10 years or more to form. The chemistry is so slow, so steady, that each layer records subtle changes in the water temperature and chemistry, creating a chronological record within the pearl structure, a diary written in calcium and protein. In the world of gemstones, the formation of turquoise is a slow chemical process that occurs in arid regions where copper-bearing minerals meet groundwater rich in phosphorus and aluminum. Turquoise is a hydrated phosphate of copper and aluminum, and it forms when slightly acidic groundwater percolates through rocks containing copper deposits, dissolving small amounts of copper ions. When this copper-rich water then encounters aluminum-bearing rocks and phosphate sources, often from the decomposition of apatite minerals, the conditions become right for turquoise to precipitate in veins and nodules. The reaction is slow because the groundwater moves gradually through tiny pores and fractures, and the concentrations of the necessary ions are usually quite low. The distinctive blue color comes from copper, while green varieties contain more iron. In the American Southwest, turquoise deposits have been forming for millions of years, the chemistry proceeding at a pace dictated by the slow movement of water through desert stone. Each piece of turquoise is the product of countless small precipitation events, water delivering ions molecule by molecule, building color and structure in the patient darkness underground. The slow oxidation of sulfide minerals in abandoned mines creates a phenomenon called acid mine drainage, a chemical process that can continue for decades or even centuries after mining operations cease. Minerals like pyrite, iron sulfide, are stable when buried deep underground, away from oxygen and water. But when mining exposes these minerals to air and moisture, oxidation begins. The sulfide slowly reacts with oxygen and water to form sulfuric acid and dissolve iron. This is not a quick reaction. It proceeds steadily, year after year, as rainwater and groundwater continue to contact the exposed mineral surfaces. The resulting acidic water, often bright orange or red from dissolved iron, can flow from mine sites for generations, slowly acidifying streams and affecting ecosystems far downstream. The chemistry is relentless but not rapid, a reminder that some reactions, once begun, continue at their own pace regardless of human intentions. Remediation efforts focus on slowing or stopping the contact between minerals, water, and oxygen, but the chemistry itself cannot be hurried to completion. It will finish in its own time, when the last of the sulfide minerals has been oxidized, a process that may outlast many human lifetimes. In the conservation of artwork, the slow polymerization and cross-linking of oil paints continues long after an artist sets down the brush. Oil paints are made by suspending pigments in drying oils, typically linseed oil, which contains triglycerides with unsaturated fatty acid chains. When exposed to air, these fatty acids undergo a slow oxidation and polymerization, forming cross-linked networks that transform the liquid oil into a solid film. This process, called autoxidation, begins quickly but continues slowly for years, even decades. A painting may feel dry to the touch within days or weeks, but the chemical curing continues in the deeper layers of paint, gradually increasing hardness and changing the mechanical properties of the film. Old master paintings are still, in a chemical sense, slowly curing centuries after their creation. The reaction rate depends on temperature, humidity, and the specific oils and pigments used. Some pigments, like lead white, actually catalyze the curing process, while others slow it down. Conservators must understand this slow chemistry when cleaning or restoring paintings, knowing that the surface they touch is not chemically inert, but still slowly transforming, still engage in reactions that began when the paint was first applied. The formation of natural cement in certain geological formations demonstrates how slow chemical reactions can create materials of remarkable strength. In some sedimentary deposits, silica dissolved in groundwater slowly precipitates between sand grains, forming a natural cement that binds them into solid rock, a process called silica cementation. The silica, often in the form of quartz, precipitates from solution when conditions change, perhaps due to evaporation, cooling, or shifts in pH. This happens extraordinarily slowly, molecule by molecule, as groundwater moves through the porous sediment. The result is a rock-like quartzite or silicified sandstone, where the grains are locked together by crystalline silica that grew in the spaces between them. The process can take millions of years, and the resulting rock can be harder than the original sand grains themselves. Similarly, calcium carbonate can cement sediments together, forming limestone conglomerates and other carbonate-cemented rocks. The chemistry is so gradual that it records the patient flow of water through stone, a liquid archive of chemical conditions that persisted long enough to build solid rock from loose sediment. In the realm of food chemistry, the Maillard reaction proceeds slowly at low temperatures, creating depth of flavor in foods that are aged or cooked gently over long periods. The Maillard reaction is a complex series of chemical reactions between amino acids and reducing sugars, producing hundreds of flavor and aroma compounds, as well as brown pigments. At high temperatures, this reaction happens quickly, as in the searing of meat or the toasting of bread. But at lower temperatures, the same chemistry unfolds slowly, contributing to the flavor development in aged cheeses, slow-roasted meats, and toasted grains. In the production of dark beers and certain malts, grains are kilned at moderate temperatures for extended periods, allowing Maillard reactions to proceed slowly and develop complex, layered flavors without burning. The same chemistry occurs in the aging of certain soy sauces and miso pastes, where months or years of fermentation at ambient temperatures allow Maillard products to accumulate gradually. The slow version of this reaction produces different ratios of flavor compounds than the fast, high-heat version, resulting in subtler, more nuanced tastes. There is a chemical reason why slow-cooked foods often taste richer and more complex. The reactions have had time to explore more pathways, to build a wider array of molecules, each contributing its small voice to the overall flavor. The weathering of granite, one of the most durable rocks on Earth, is a slow chemical process that eventually reduces mountains to sand and clay. Granite is composed primarily of quartz, feldspar, and mica, minerals that form deep underground under high pressure and temperature. When exposed at the surface, these minerals are no longer in equilibrium with their environment, and they begin to break down chemically. Feldspar, in particular, undergoes a slow hydrolysis reaction in the presence of slightly acidic rainwater, gradually transforming into clay minerals like kaolinite. The reaction releases potassium, sodium, and calcium ions into solution, which are carried away by water, while the aluminum and silicon reorganize into the layered structure of clay. This process is so slow that a granite outcrop may persist for millions of years, shedding grains and clay particles at a nearly imperceptible rate. Yet, over geological time, this patient chemistry is one of the primary processes that shapes landscapes, reducing mountain ranges to rolling hills and eventually to flat plains. The quartz grains, more resistant to chemical weathering, become sand, while the feldspar becomes clay, and together they form the sediments that will eventually become new sedimentary rocks. The cycle is powered by chemistry that never hurries, never pauses, simply continues at its own steady pace as long as water and rock remain in contact. In the human brain, the slow accumulation of certain proteins is associated with aging and neurodegenerative conditions, a reminder that not all slow chemistry is benign. Proteins like beta amyloid and tau can, over years or decades, gradually misfold and aggregate, forming plaques and tangles that interfere with neuronal function. These are not rapid processes. They unfold across much of a human lifetime, influenced by genetics, environment, and chance. The chemistry involves subtle changes in protein structure, where a normally soluble protein shifts to an insoluble form that tends to stick to other misfolded proteins. Once started, the process can be self-perpetuating, as aggregates serve as seeds for further aggregation. Research into these slow reactions seeks to understand how they begin, why they accelerate in some individuals, and how they might be slowed or stopped. The pace of these changes is such that interventions, if effective, might need to begin years or decades before symptoms appear, targeting chemistry that is already quietly underway in the microscopic spaces between neurons. It is a sobering reminder that the slow reactions within us are not all as benign as bone remodeling or collagen maintenance, and that understanding slow chemistry is essential to understanding aging itself. The formation of coal deposits from ancient peat is a chemical transformation that spans tens to hundreds of millions of years, one of the slowest progressions in geochemistry. We have touched on this before, but there are deeper layers to explore. As peat is buried beneath accumulating sediments, it is subjected to increasing pressure and temperature, a process called coalification. The organic matter, originally composed of plant tissues rich in cellulose, lignin, and other complex molecules, undergoes a series of chemical changes. Water and volatile compounds are gradually expelled, and the proportion of carbon increases. Peat becomes lignite, then subbituminous coal, then bituminous coal, and finally, under the most extreme conditions, anthracite. Each stage involves the slow breaking of chemical bonds and the rearrangement of carbon atoms into more stable, aromatic structures. The process is driven by heat and pressure, but it is not fast even by geological standards. It takes millions of years for peat to become bituminous coal, and tens of millions more to reach anthracite grade. The chemistry is so slow that coal deposits preserve not just carbon, but also chemical signatures of the ancient atmosphere, the types of plants that grew, and the conditions of burial. Each seam of coal is a chemical archive, a record of slow transformation that began in swamps and forests that vanished eons ago. The slow dissolution of bone in acidic environments is a process that archaeologists and forensic scientists must consider when interpreting burial sites. Bone is primarily composed of hydroxyapatite, which is relatively stable in neutral or alkaline soils but slowly dissolves in acidic conditions. In acidic soils, hydrogen ions from organic acids and carbonic acid gradually react with the calcium phosphate, releasing calcium and phosphate ions into the soil solution. The rate of dissolution depends on pH, temperature, moisture, and the presence of microorganisms that produce additional acids. In highly acidic environments, bones can completely dissolve within decades or centuries, leaving no trace. In neutral or alkaline soils, bones can persist for thousands or even millions of years. This slow chemistry determines what evidence remains of past lives, which graves yield skeletons, and which yield only stains in the soil where bones once lay. The dissolution is not uniform. Dense cortical bone dissolves more slowly than porous trabecular bone, and teeth, with their enamel coating, are often the most resistant. Understanding this slow, acid-based chemistry allows scientists to reconstruct burial conditions and estimate how long remains have been in the ground, reading the chemical history written in what has been preserved and what has been lost. In the deep ocean, the slow formation of ferromanganese nodules on the seafloor is one of the most patient chemical processes known. These nodules, sometimes called manganese nodules or polymetallic nodules, grow on the abyssal plains, far from any continental influence. They form by the slow precipitation of iron and manganese oxides from seawater, along with trace amounts of nickel, copper, cobalt, and other metals. The exact mechanism is still debated, but it involves the oxidation of dissolved manganese and iron, which are present in seawater at very low concentrations. The metals precipitate around a nucleus, often a shark tooth or a fragment of shell, building up concentric layers over time. The growth rate is astonishingly slow, typically only a few millimeters per million years. A nodule the size of a potato may have been growing for tens of millions of years, quietly accreting metal oxides in the cold, dark, still water of the deep sea. The chemistry is so gradual that the nodules record changes in ocean chemistry over geological time. Their layers like tree rings, each one a snapshot of ancient seawater composition. They rest on the seafloor in vast fields, millions of them, each one a testament to the slowest chemical precipitation on Earth. The aging of rubber, a process called perishing, is a slow chemical degradation that affects everything from car tires to elastic bands. Rubber, whether natural or synthetic, is a polymer with long chains of repeating units, often containing carbon-carbon double bonds. These double bonds are vulnerable to attack by oxygen and ozone, which slowly break the polymer chains in a process called oxidative degradation. The reaction is accelerated by heat, light, and mechanical stress, but even under mild conditions, it proceeds steadily over years. Natural rubber exposed to air will gradually become brittle and crack as the polymer chains are severed and cross-linking increases. Ozone is particularly aggressive, attacking double bonds and causing surface cracking in a pattern called ozone cracking. Antioxidants and antioxidants are added to rubber products to slow this chemistry, but they cannot stop it entirely. Over time, they are consumed and the degradation continues. An old rubber band that snaps at the slightest stretch, a tire that develops cracks even without much use. These are the visible results of slow chemical reactions that have been quietly breaking bonds for years. The chemistry is patient and inevitable, a reminder that even flexible, resilient materials are not immune to the slow work of oxidation. In the conservation of historic buildings, the slow sulfation of limestone and marble is a major concern, especially in urban environments with air pollution. Limestone and marble are both forms of calcium carbonate, and they react slowly with sulfur dioxide in the air, a pollutant produced by burning fossil fuels. The sulfur dioxide dissolves in moisture on the stone surface, forming sulfurous acid, which then oxidizes to sulfuric acid. This acid reacts with a calcium carbonate to form calcium sulfate, or gypsum. The gypsum forms a white or gray crust on the stone surface, and because it is more soluble than the original carbonate, it can be washed away by rain, gradually eroding the stone. The reaction is slow, taking years or decades to produce visible damage, but over a century or more, it can obliterate fine carved details on sculptures and architectural ornaments. The chemistry is insidious because it proceeds even at low pollutant concentrations, and because the gypsum crust can trap dirt and pollutants, accelerating further decay. Conservators work to slow this process by cleaning surfaces, applying protective coatings, and advocating for cleaner air. But the chemistry itself, once begun, continues as long as sulfur dioxide and moisture are present, a slow erasure of history written in acid and salt. The slow hydration of certain minerals, such as anhydrite transforming into gypsum, is a chemical process that can cause significant geological and engineering effects. Anhydrite is anhydrous calcium sulfate, a mineral that forms in evaporite deposits where seawater has evaporated under arid conditions. When anhydrite is exposed to water, either from groundwater or from changes in environmental conditions, it slowly absorbs water molecules and transforms into gypsum, hydrated calcium sulfate. This reaction involves the incorporation of 2 water molecules per formula unit, and it causes a significant increase in volume, about 30 to 50%. The transformation is slow, taking years to decades depending on temperature, water availability, and the surface area of the mineral. But the volume expansion can generate tremendous forces, capable of heaving up overlying rock layers, buckling roadbeds, and damaging building foundations. In some regions, the slow hydration of anhydrite in the subsurface has caused ongoing ground deformation, a gradual swelling that continues as long as water is available. The chemistry is simple, just the addition of water, but the physical consequences are dramatic, a reminder that slow reactions can still exert powerful effects on the world around us. In the realm of atmospheric chemistry, the slow breakdown of certain refrigerants and industrial chemicals in the stratosphere has had profound effects on the ozone layer. Chlorofluorocarbons, or CFCs, are remarkably stable compounds that do not break down in the lower atmosphere. They can persist for decades, or even a century, slowly drifting upward until they reach the stratosphere. There, intense ultraviolet light finally breaks the carbon-chlorine bonds, releasing chlorine atoms. These chlorine atoms then participate in catalytic cycles that destroy ozone molecules, with a single chlorine atom capable of breaking down thousands of ozone molecules before it is finally removed from the stratosphere. The entire process, from the release of a CFC molecule at the surface to its breakdown in the stratosphere, and the subsequent ozone destruction unfolds over decades. This slow chemistry was not understood when CFCs were first introduced, and by the time the connection to ozone depletion was discovered, millions of tons of these compounds had already been released. Even after the Montreal Protocol phased out CFC production, the compounds already in the atmosphere continued their slow journey upward, and the ozone layer is only now, decades later, beginning to recover. It is a powerful example of how slow chemical reactions can have global consequences, and how the effects of human activities can persist long after the activities themselves have ceased. The formation of kidney stones is a slow precipitation process that occurs within the urinary system, often over months or years. Most kidney stones are composed of calcium oxalate or calcium phosphate, though other compositions exist. The chemistry begins when urine becomes supersaturated with these minerals, meaning that the concentration of dissolved ions exceeds the solubility limit. Under these conditions, tiny crystals can begin to form, a process called nucleation. These initial crystals are often microscopic and may be flushed out of the system without causing problems. But if they remain in the kidney, they can grow slowly as more mineral precipitates onto their surfaces. The growth rate depends on urine composition, pH, flow rate, and the presence of substances that either promote or inhibit crystallization. A stone may grow for months or years before it becomes large enough to cause symptoms. The chemistry is influenced by diet, hydration, genetics, and metabolic factors, and understanding it is key to both preventing and treating kidney stones. The slow accretion of mineral, layer upon layer, mirrors the formation of pearls or cave formations. But in this case, the result is painful rather than beautiful, a reminder that the same chemical principles operate in very different contexts. The slow conversion of amorphous silica to crystalline quartz is a process that occurs in sediments and volcanic rocks over geological time. When silica first precipitates from solution, it is often in an amorphous or poorly crystalline form, such as opal or silica gel. This amorphous silica is not in its most stable state. Given enough time, it will slowly reorganize into crystalline quartz, which is more thermodynamically stable. The transformation involves the breaking and reforming of silicon-oxygen bonds, allowing the atoms to arrange themselves into the regular, repeating pattern of a crystal. The process is accelerated by heat and the presence of water, but even under favorable conditions, it is slow, taking thousands to millions of years. Opal, for example, can slowly dehydrate and crystallize over geological time, losing its play of color as the amorphous structure is replaced by crystalline quartz. In sedimentary rocks, amorphous silica cement may gradually transform to quartz, increasing the rock's hardness and durability. The chemistry is driven by the system's tendency toward lower energy states, a thermodynamic patience that operates on timescales far beyond human perception. The slow oxidation of organic matter in landfills is a chemical process that continues for decades after a landfill is closed. When organic waste, such as food scraps, paper, and yard waste, is buried in a landfill, it begins to decompose through a combination of aerobic and anaerobic processes. In the presence of oxygen, aerobic bacteria oxidize the organic matter relatively quickly, producing carbon dioxide and water. But in the deeper, oxygen-poor layers of a landfill, anaerobic bacteria take over, and the chemistry slows down considerably. These bacteria break down complex organic molecules into simpler compounds, eventually producing methane and carbon dioxide. The process can take decades, and methane production from a landfill may continue for 20 to 50 years or more after the last waste is deposited. The slow chemistry creates challenges for landfill management, as the methane must be captured or vented to prevent explosions and reduce greenhouse gas emissions. Some landfills harness this slow reaction, collecting the methane and using it as a fuel source, turning a waste problem into an energy resource. The chemistry is a reminder that disposal is not the end of the story. The reactions we set in motion by burying organic matter continue long after we have moved on. In the world of art conservation, the slow migration of oils and solvents through layers of paint and varnish is a chemical process that can affect the appearance and stability of paintings. Oil paints, as they cure, can develop networks of microscopic channels and pores through which small molecules can slowly diffuse. Over decades or centuries, components of the paint medium, such as free fatty acids or low molecular weight polymers, can migrate to the surface, sometimes forming a hazy or sticky layer. Similarly, if a painting is cleaned with solvents, those solvents can penetrate into the paint layers and then slowly diffuse back out over months or years, potentially carrying dissolved materials with them. Varnishes applied to protect paintings can also undergo slow chemical changes, such as oxidation and cross-linking, which can cause them to yellow, darken, or become brittle. Conservators must understand these slow diffusion and reaction processes to make informed decisions about cleaning, varnishing, and storing artworks. The chemistry is subtle and slow, but over the lifespan of a painting, it can significantly alter what we see and how the artwork is preserved for future generations. The slow release of radon gas from rocks and soil is a natural radioactive decay process that occurs continuously in the environment. Radon is a noble gas produced by the decay of radium, which in turn comes from the decay of uranium present in trace amounts in many rocks and soils. The decay of radium to radon is a nuclear reaction, not a chemical one, but the subsequent behavior of radon is governed by chemistry and physics. Radon atoms, once formed, can diffuse through soil and rock, moving slowly through pore spaces and fractures until they reach the atmosphere or accumulate in enclosed spaces like basements. The rate of radon release depends on the uranium content of the rock, the porosity and permeability of the soil, and environmental factors like moisture and temperature. Radon itself is radioactive, with a half-life of about 4 days, so it decays as it moves, producing radioactive decay products that can pose health risks if inhaled. The entire process, from the slow decay of uranium deep in the earth to the diffusion of radon into buildings, unfolds over timescales ranging from seconds to billions of years. It is a natural background process, a slow emanation of radioactivity that has been occurring since the earth formed, a reminder that even the ground beneath us is chemically and physically active in ways we rarely perceive. The formation of natural glass, such as obsidian, involves the rapid cooling of lava, but the subsequent slow devitrification of that glass is a chemical process that can take thousands to millions of years. Obsidian forms when silica-rich lava cools so quickly that the atoms do not have time to arrange into a crystalline structure. Instead, they freeze into an amorphous, glassy state. This glass is not thermodynamically stable. Given time, the atoms will slowly reorganize into crystals, a process called devitrification. The rate depends on temperature and the composition of the glass, but at surface temperatures, it is extremely slow. Ancient obsidian artifacts and natural obsidian flows can show signs of devitrification, with tiny crystals beginning to form within the glass, often visible as a cloudy or mottled appearance. The chemistry is the same as the amorphous silica to quartz transformation. The system is moving toward a more stable, lower energy state, but the movement is so slow that obsidian can remain glassy for millions of years. It is a frozen moment of volcanic violence, held in a metastable state by the slowness of the chemistry that would, eventually, erase its glassy nature. The slow corrosion of lead in historical plumbing and artifacts is a chemical process that has both preserved and endangered cultural heritage. Lead is a soft, malleable metal that was widely used in ancient Rome for water pipes, and in later periods for roofing, weights, and seals. When lead is exposed to water and air, it slowly oxidizes, forming a series of corrosion products including lead oxide, lead carbonate, and lead sulfate, depending on the environment. In the presence of hard water, which contains calcium and carbonate ions, lead pipes can develop a protective coating of lead carbonate that actually slows further corrosion, a process similar to the patina on copper. However, in soft or acidic water, lead can dissolve more readily, leading to lead contamination of drinking water, a serious health concern. The corrosion of lead in archaeological contexts is usually slow, and lead artifacts can survive for thousands of years, often with a thick, pale gray corrosion crust. The chemistry is complex, involving not just oxidation, but also reactions with sulfur, chlorine, and organic acids in the soil. Understanding this slow corrosion is important for both conserving historical objects and for addressing modern lead contamination issues in aging infrastructure. The slow polymerization of certain monomers in storage is a chemical process that can pose safety hazards in industrial settings. Some chemicals, such as styrene, acrylates, and vinyl acetate, are stored and transported as liquids, but have a tendency to slowly polymerize, forming solid polymers. This polymerization is usually initiated by heat, light, or trace amounts of oxygen and free radicals. To prevent it, manufacturers add inhibitors, chemicals that react with free radicals and stop the polymerization chain reaction. However, these inhibitors are slowly consumed over time, and if the storage conditions are not ideal, polymerization can begin. The reaction is exothermic, meaning it releases heat, and once started, the heat can accelerate the reaction, potentially leading to a runaway polymerization that generates enough heat and pressure to rupture containers. The chemistry is slow at first, perhaps taking months or years to become noticeable, but it can suddenly accelerate. This is why such chemicals are stored in cool, dark conditions and why their inhibitor levels are monitored. It is a reminder that even chemicals sitting quietly in a tank are not necessarily inert. Slow reactions may be underway, and vigilance is required to keep them slow. The gradual leaching of nutrients from soil is a slow chemical process that affects soil fertility and requires careful management in agriculture. Rainwater percolating through soil can slowly dissolve and carry away essential nutrients such as nitrate, potassium, calcium, and magnesium. This process, called leaching, is essentially a slow extraction, with water acting as the solvent. The rate of leaching depends on soil texture, the amount of rainfall, the presence of organic matter, and the chemical form of the nutrients. Sandy soils, with their large pore spaces, allow water to move quickly and leach nutrients rapidly. Clay soils, with their fine particles and greater capacity to bind nutrients, leach more slowly. Over time, if nutrients are not replenished through fertilization, organic matter decomposition, or natural mineral weathering, soils can become depleted, less able to support plant growth. The chemistry is a balance between inputs and losses, and understanding the slow leaching processes is essential for sustainable agriculture. Ancient agricultural societies learned to manage this through crop rotation, fallowing, and the addition of manure and compost, working with the slow chemistry of the soil rather than against it. The slow reaction between atmospheric nitrogen and oxygen during lightning strikes produces small amounts of nitrogen oxides, which then slowly dissolve in rainwater to form nitric acid. This is one of the natural pathways by which atmospheric nitrogen is fixed into a form that plants can use. Lightning provides the energy to break the strong triple bond in nitrogen gas, allowing nitrogen and oxygen to combine. The nitrogen oxides produced are then oxidized further in the atmosphere and dissolve in water droplets, eventually falling as rain and entering the soil as nitrate. The entire process, from lightning flash to nitrate in the soil, involves multiple slow steps, particularly the atmospheric oxidation and the gradual descent of rain. Before the industrial production of nitrogen fertilizers, this natural fixation, along with biological nitrogen fixation by bacteria, was the primary source of available nitrogen for ecosystems. The chemistry is a gift of the atmosphere, a slow trickle of fertility delivered by storms, a reminder that even violent events like lightning are part of slow, essential chemical cycles. And so the chemistry continues, process after process, each unfolding at its own pace, each contributing to the slow transformation of matter and energy in the world around us. The reactions do not rush, do not demand attention, yet they shape everything: landscapes, ecosystems, artworks, our own bodies. There is a deep restfulness in this knowledge, a sense that the universe is patient, that change happens whether we watch or not, whether we worry or not. The chemistry asks nothing of us but time. The slow transformation of atmospheric methane offers another quiet lesson in patient chemistry. Methane molecules released into the air do not linger forever, though their journey toward breakdown unfolds across years rather than moments. Hydroxyl radicals, those invisible scavengers of the atmosphere, gradually find and dismantle methane molecules through a series of careful oxidation steps. Each reaction proceeds gently, without haste, converting methane first to formaldehyde, then to formic acid, and finally to carbon dioxide and water. The entire cascade takes roughly a decade on average, a span of time that allows methane to drift across continents and oceans before its chemical identity dissolves into simpler forms. This slow removal process shapes our climate in profound ways, governing how long each methane molecule can trap heat before returning to the atmospheric commons as something else entirely. The formation of natural cement in sedimentary rocks whispers of chemistry that binds the world together grain by grain. When sand settles at the bottom of ancient seas or rivers, the spaces between particles slowly fill with mineral solutions carried by groundwater. Silica, calcium carbonate, or iron oxides precipitate from these solutions over thousands of years, crystallizing in the tiny gaps and gluing each sand grain to its neighbors. The process demands patience beyond human measure, as each molecule must find its place in the growing crystal lattice, one addition at a time. Temperature, pressure, and the chemistry of the percolating water all influence which minerals will serve as nature's glue. Eventually, loose sediment becomes solid sandstone, a transformation so gradual that no single moment marks the boundary between sand and stone. This quiet cementation creates the layered rocks that form cliffs and canyons, each grain held in place by chemical bonds that formed while empires rose and fell above. The slow oxidation of sulfide minerals and mine tailings creates a persistent environmental challenge that unfolds across decades. When mining operations expose rocks rich in iron sulfides like pyrite to air and water, oxidation begins immediately but proceeds at a measured pace. Bacteria often accelerate the process, but even with their help, the conversion of solid sulfide to dissolved sulfate takes years to complete. As sulfides oxidize, they release sulfuric acid and dissolved metals into surrounding water, creating the phenomenon known as acid mine drainage. This acidic, metal-laden water can persist for generations after mining operations cease, slowly leaching from tailings piles and underground workings. The chemistry continues as long as sulfide minerals remain exposed to oxygen and moisture, a reminder that some reactions, once initiated, cannot easily be stopped. Remediation efforts must account for this persistence, designing systems that will function not just for years, but for the many decades required for the sulfides to fully oxidize and neutralize. The gradual formation of clay minerals for volcanic ash illustrates chemistry's power to transform fire into fertility. When volcanic eruptions scatter fine ash across landscapes, that glassy material begins a slow metamorphosis the moment it settles. Water percolating through the ash dissolves some components while leaving others behind, initiating a complex series of reactions that restructure the mineral's atomic arrangement. Over hundreds to thousands of years, the volcanic glass transforms into clay minerals, their layered structures forming molecule by patient molecule. The specific type of clay that emerges depends on the chemistry of the original ash, the acidity of the water, and the climate of the region. Volcanic soils owe much of their legendary fertility to this slow transformation, as the newly formed clays provide excellent structure and nutrient-holding capacity. The process continues even now in volcanic regions around the world, turning yesterday's catastrophe into tomorrow's farmland through chemistry that never rushes. The slow hydrolysis of complex carbohydrates in aging plant material reveals how nature dismantles what it once built. Cellulose and hemicellulose, the structural polymers that give plants their rigidity, begin to break down the moment a leaf falls or a tree dies. Water molecules slowly insert themselves into the chemical bonds linking sugar units together, cleaving the long chains into shorter fragments. This hydrolysis proceeds slowly in dry conditions, faster in wet ones, but always at a pace measured in months or years rather than days. Fungi and bacteria accelerate the process, but even in their absence, the chemistry continues through purely abiotic mechanisms. The breakdown releases simple sugars back into the environment, completing the carbon cycle one bond at a time. In forests, This slow decomposition creates the spongy layer of partially decayed material that holds moisture and nurtures new growth, a testament to chemistry's role in recycling life. The gradual dissolution of bone in acidic soils demonstrates how even our most durable tissues eventually return to the earth. Bone consists largely of calcium phosphate crystals embedded in a protein matrix, a composite material designed for strength and longevity. But when buried in soils with low pH, the calcium phosphate begins to dissolve slowly, releasing calcium and phosphate ions into the surrounding groundwater. The protein component, mostly collagen, degrades through hydrolysis and microbial action, though this too proceeds gradually over years or decades. In very acidic conditions, bones can disappear entirely within a century, while in neutral or alkaline soils, they may persist for thousands of years. This slow dissolution explains why archaeological sites in some regions yield abundant skeletal remains, while others preserve almost nothing. The chemistry of the burial environment determines whether bones endure or fade, a process so gradual that it maps the patient work of countless water molecules finding and breaking chemical bonds. The formation of travertine terraces at hot springs offers a visible record of slow precipitation chemistry. Water heated deep underground dissolves calcium carbonate from limestone layers, becoming saturated with dissolved minerals. When this water emerges at the surface and cools, it can no longer hold as much calcium carbonate in solution, and the excess begins to precipitate. Each molecule of calcite that crystallizes from the cooling water adds to the growing terraces, building the distinctive step formation seen at places like Mammoth Hot Springs or Pamukale. The process continues day after day, year after year, with visible growth occurring over decades. The terraces record changes in water chemistry, flow patterns, and even climate, their layers preserving information like the rings of a tree. This slow construction creates landscapes of surreal beauty, each delicate rim and pool the product of chemistry that works without ceasing but never in haste. The slow reaction between atmospheric nitrogen and oxygen during lightning strikes represents one of nature's pathways for nitrogen fixation. The intense heat of a lightning bolt, reaching temperatures higher than the sun's surface, provides enough energy to break the extraordinarily strong triple bond holding nitrogen molecules together. Once separated, nitrogen atoms can combine with oxygen to form nitrogen oxides, compounds that dissolve in rain and eventually reach the soil as nitrates. This process occurs in a flash, but the overall contribution to nitrogen fixation happens slowly because lightning strikes, while dramatic, are relatively rare events at any given location. Over a year, lightning contributes a small but meaningful fraction of the nitrogen that plants need, supplementing the much larger contribution from nitrogen-fixing bacteria. The chemistry initiated in a moment of electrical violence continues as the nitrogen oxides drift through the atmosphere, react with water, and slowly settle to Earth, completing a journey from air to soil that can take days or weeks. The gradual transformation of recently formed basalt into soil reveals how water and carbon dioxide collaborate to break down rock. Basalt, rich in iron and magnesium silicates, reacts slowly with carbonic acid formed when rainwater absorbs atmospheric carbon dioxide. This weak acid gradually dissolves minerals, releasing ions and leaving behind clay minerals and iron oxides. The process proceeds fastest in warm, wet climates where water is abundant and chemical reactions accelerate with heat. Even so, converting solid basalt into soil takes thousands of years, a testament to the strength of silicate bonds and the patience of weathering chemistry. The resulting soils are often remarkably fertile, rich in minerals released from the parent rock. Volcanic islands demonstrate this transformation beautifully. Their young basalt flows slowly, softening into soil that supports lush vegetation, each plant rooted in the chemical breakdown of stone. The slow polymerization of natural latex in living rubber trees illustrates chemistry that serves life's purposes. Rubber trees produce latex as a defensive fluid, a sticky substance that seals wounds and deters herbivores. The latex contains isoprene units that slowly polymerize into long chains, forming the elastic polymer we call natural rubber. This polymerization continues even after the latex is harvested, though traditional processing methods accelerate and control the reaction through vulcanization. In the tree, the chemistry proceeds at a measured pace, creating just enough polymer to maintain the latex's protective properties without solidifying prematurely. The slow natural polymerization allows the tree to store liquid latex in specialized vessels, ready to flow when needed. This patient chemistry, refined over millions of years of evolution, produces one of nature's most remarkable materials, all without heat or pressure or industrial catalysts. The gradual formation of phosphorite deposits from ancient marine sediments reveals chemistry that concentrates a vital nutrient. Phosphorus, essential for all life, occurs in relatively low concentrations in seawater. But in certain conditions, especially where deep, nutrient-rich waters upwell to the surface, phosphorus can accumulate in sediments as organic matter settles and decomposes. Over millions of years, chemical reactions transform this phosphorus-enriched sediment into phosphorite rock, a process involving dissolution, reprecipitation, and gradual concentration of phosphate minerals. The chemistry proceeds so slowly that phosphorite deposits record ancient ocean conditions, preserving evidence of long-vanished ecosystems. These deposits, formed by patient accumulation and transformation, now provide most of the phosphorus used in modern agriculture, a gift from ancient seas that took geological ages to prepare. The slow oxidation of reduced iron in groundwater creates distinctive patterns in aquifers and springs. Deep underground, where oxygen is scarce, iron often exists in its reduced ferrous form, dissolved and invisible in water. When this water reaches the surface or encounters oxygen-rich zones, the iron slowly oxidizes to its ferric form, which is far less soluble. The oxidized iron precipitates as rust-color hydroxides, staining rocks and sediments, and sometimes forming substantial deposits. This oxidation can take hours or days, depending on pH and oxygen levels, a leisurely pace compared to many chemical reactions. The process creates the characteristic orange or red staining seen around springs and seeps, a visible signature of chemistry in progress. In some cases, bacteria accelerate the oxidation, harvesting energy from the reaction, but even without biological assistance, the chemistry proceeds steadily, painting the landscape with iron's transformation. The formation of natural glass from volcanic lava and its subsequent slow devitrification tells a story of order emerging from chaos. When lava cools so quickly that crystals cannot form, it solidifies as obsidian, a volcanic glass with atoms frozen in disordered arrangement. This glass is not thermodynamically stable. Given time, the atoms would prefer to arrange themselves into orderly crystals. And so begins a transformation so slow it requires millennia to become visible. Water molecules penetrating along tiny cracks facilitate the process, providing the mobility needed for atoms to reorganize. Gradually, crystals begin to grow within the glass, creating patterns called snowflake obsidian or producing a dull, crystalline texture. The devitrification proceeds so slowly that obsidian artifacts thousands of years old still retain their glassy luster. Yet the chemistry continues, patient and inexorable, slowly converting disorder into the crystalline arrangement that represents a lower energy state. The slow breakdown of chlorofluorocarbons in the upper atmosphere demonstrates chemistry's role in planetary scale environmental change. CFCs, once widely used as refrigerants and propellants, are remarkably stable in the lower atmosphere, persisting for decades or even centuries. But when they eventually drift into the stratosphere, ultraviolet light breaks them apart, releasing chlorine atoms that catalyze the destruction of ozone molecules. Each chlorine atom can destroy thousands of ozone molecules before it finally reacts with something else and becomes inactive. The entire process, from CFC release to chlorine deactivation, unfolds over many decades, creating a long delay between cause and effect. This slow chemistry explains why the ozone layer continues to recover gradually, even though CFC emissions have been largely eliminated. The patient pace of stratospheric chemistry means that decisions made generations ago still influence the atmosphere today, and the healing process will continue for decades to come. The gradual formation of secondary minerals in concrete structures reveals chemistry that continues long after construction ends. Fresh concrete is highly alkaline, with a pH often above 12, creating an environment that protects embedded steel from corrosion. But carbon dioxide from the air slowly diffuses into the concrete, reacting with calcium hydroxide to form calcium carbonate in a process called carbonation. This reaction gradually reduces the pH, progressing inward from the surface at a rate of a few millimeters per year. The chemistry proceeds steadily, year after year, slowly changing the concrete's properties. In the carbonated zone, the concrete becomes slightly denser and stronger, but the lower pH means that any steel reinforcement is no longer protected from rust. This slow transformation influences the lifespan of concrete structures, a reminder that chemistry continues to reshape our built environment long after the work crews have departed. The slow dissolution of silica from diatom shells on the ocean floor illustrates chemistry that recycles minerals through deep time. Diatoms, microscopic algae with intricate glass shells, sink to the seafloor when they die, accumulating in vast deposits. Silica is not very soluble in seawater, but it does dissolve slowly, especially under the pressure and cold of the deep ocean. Over thousands of years, these delicate shells gradually disappear, returning their silica to the water column, where it can be used by new generations of diatoms. The dissolution rate depends on temperature, pressure, and the saturation state of the surrounding water, but it always proceeds slowly, measured in millimeters per millennium. This patient recycling of silica sustains the ocean's diatom populations, connecting life across vast spans of time through chemistry that never hurries. The formation of natural sulfur deposits through the slow reduction of sulfate minerals demonstrates chemistry's ability to transform abundant compounds into pure elements. In certain geological settings, bacteria reduce dissolved sulfate to hydrogen sulfide, which can then react with oxygen or other compounds to precipitate elemental sulfur. This process occurs in salt domes, hot springs, and volcanic areas, proceeding slowly over thousands of years. The chemistry requires specific conditions: the presence of sulfate, organic matter to fuel bacterial metabolism, and an environment where hydrogen sulfide can be oxidized before escaping. When these conditions align, sulfur accumulates gradually, forming deposits that can be quite pure. These natural sulfur deposits, built by patient chemistry, supplied most of the world's sulfur before industrial processes made extraction from petroleum more economical. The slow transformation of organic matter into kerogen in sedimentary rocks represents an intermediate stage in the formation of fossil fuels. Kerogen, a solid organic material dispersed within rocks, forms as buried organic matter undergoes chemical changes over millions of years. Heat and pressure gradually break down complex biological molecules, removing oxygen, nitrogen, and sulfur while concentrating carbon and hydrogen. The process proceeds so slowly that different stages of kerogen maturation can be identified, each representing millions of years of transformation. Given enough time and the right conditions, kerogen eventually breaks down into smaller molecules, generating petroleum or natural gas. But this final transformation requires tens to hundreds of millions of years, making it one of the slowest chemical processes on Earth. The kerogen stage can persist almost indefinitely if temperatures remain too low for further breakdown, preserving organic matter in a state of chemical suspended animation. The gradual oxidation of pyrite in museum specimens reveals chemistry that continues even in controlled environments. Pyrite, fool's gold, is chemically unstable in the presence of moisture and oxygen, though the reaction proceeds slowly at room temperature. Museum collections sometimes discover that pyrite specimens or fossils preserved in pyrite-rich rock begin to deteriorate, developing a white powder of sulfate minerals and releasing sulfuric acid that damages labels and storage materials. The oxidation can take years to become noticeable, proceeding silently in drawers and display cases. This slow chemistry poses challenges for conservation, requiring careful monitoring and sometimes special storage conditions to slow the inevitable reaction. The phenomenon reminds us that chemistry respects no boundaries, continuing its patient work even in institutions dedicated to preservation. The slow formation of natural zeolites from volcanic ash in alkaline lake environments demonstrates chemistry's ability to create ordered structures from disordered starting materials. Zeolites are crystalline aluminosilicates with regular pore structures, valuable for their ability to selectively absorb molecules. They form when volcanic glass reacts with alkaline water over thousands of years, dissolving and reprecipitating in more stable crystalline forms. The specific type of zeolite that forms depends on the chemistry of the water, the composition of the ash, and the temperature. The transformation proceeds slowly, molecule by molecule, building intricate crystal structures with mathematical precision. Natural zeolite deposits, formed through this patient chemistry, find use in water purification, agriculture, and industry. Their molecular sieves created by reactions that required millennia to complete. The gradual replacement of wood by minerals in petrified forests illustrates chemistry's ability to preserve form while completely changing substance. When trees are buried rapidly in sediment, groundwater carrying dissolved minerals percolates through the wood. As the wood's organic material slowly decays, minerals precipitate in the spaces left behind, often preserving cellular structure in exquisite detail. Silica is the most common replacing mineral, but calcite, pyrite, and other minerals can also participate. The process requires thousands to millions of years, as each cell must be filled and each molecule of wood carefully replaced. The resulting petrified wood looks like wood and preserves its structure, but consists entirely of stone. This transformation occurs so gradually that the delicate architecture of the original tissue remains intact, a fossil formed not through preservation, but through slow chemical substitution. The slow reaction between limestone and acid rain creates a visible record of air pollution's effects on stone monuments. Sulfur dioxide and nitrogen oxides from fossil fuel combustion dissolve in atmospheric moisture to form weak acids. When this acid rain falls on limestone or marble, it slowly dissolves the calcium carbonate, roughening surfaces and obscuring carved details. The reaction proceeds faster than natural weathering, but still takes decades to create noticeable damage. Each raindrop carries away a tiny amount of dissolved stone, a loss so small as to be imperceptible, but cumulative over years and decades. Statues and buildings that have stood for centuries show accelerated deterioration in the industrial era, their surfaces recording the slow chemical cost of atmospheric pollution. The chemistry is simple. Acid plus carbonate yields carbon dioxide and water, but the cultural and historical consequences accumulate slowly, erasing details that can never be recovered. The formation of natural niter deposits in arid caves reveals chemistry that concentrates nitrogen from bat guano and other organic sources. Bacteria decompose the organic matter, releasing ammonia that slowly oxidizes to nitrate through a series of microbial reactions. In dry cave environments where rain cannot wash the nitrates away, they accumulate over centuries as crystalline deposits of potassium nitrate or sodium nitrate. The process requires a delicate balance, enough moisture to support bacterial activity, but not enough to dissolve and remove the products. The chemistry proceeds patiently, concentrating nitrogen from countless generations of bats into deposits that humans once mined for gunpowder and fertilizer. These natural niter caves, formed by slow chemistry and darkness, represent accumulations of thousands of years, each crystal a testament to patient transformation. The slow polymerization and cross-linking of proteins in aging tissues contributes to many of the physical changes associated with growing older. Proteins in long-lived tissues like cartilage, tendons, and the lens of the eye gradually form crosslinks through various chemical reactions. Some crosslinks result from glycation, where sugars react with proteins over months and years. Others form through oxidation or through enzymatic processes that continue at low levels throughout life. These slow reactions make tissues stiffer and less flexible, contributing to joint stiffness, loss of skin elasticity, and clouding of the eye's lens. The chemistry proceeds at body temperature without catalysts, driven simply by the proximity of reactive molecules over decades. Understanding these slow reactions helps researchers develop strategies to slow or reverse some aspects of aging, working against chemistry that has been proceeding since birth. The gradual transformation of organic matter in peat bogs represents the first step toward coal formation, a process still underway in wetlands around the world. In waterlogged conditions where oxygen is scarce, plant material decomposes very slowly, accumulating faster than it decays. Anaerobic bacteria break down some components, but the overall process is sluggish, preserving much of the original plant structure. Over centuries, the accumulated plant material compresses under its own weight, squeezing out water and beginning chemical transformations that concentrate carbon. The peat darkens and becomes denser, slowly transitioning toward lignite, the lowest grade of coal. This transformation takes thousands to millions of years to complete, but it begins immediately when plant matter falls into oxygen-poor water. Modern peat bogs are windows into ancient processes, showing us the first stages of a chemical journey that, given enough time and burial, could eventually produce coal. The slow hydrolysis of aspirin in solution demonstrates why medications have expiration dates and why chemistry matters in pharmaceutical storage. Aspirin, acetylsalicylic acid, slowly reacts with water to break down into salicylic acid and acetic acid. The reaction proceeds slowly at room temperature, faster when warm, and fastest in solution. A bottle of aspirin tablets stored in a cool, dry place might remain potent for years, but the same tablets dissolved in water would degrade noticeably within weeks. The chemistry is simple hydrolysis, water molecules inserting themselves into an ester bond and cleaving it, but the reaction's slow pace makes it relevant to everyday life. The faint vinegar smell of old aspirin comes from the acetic acid produced by this gradual breakdown, a sensory signal that chemistry has been quietly at work. The formation of natural cement in fault zones through pressure solution and reprecipitation illustrates chemistry that can heal fractures in rock. When rocks are compressed along fault lines, minerals at points of high stress slowly dissolve, even though the overall rock remains solid. The dissolved material migrates through thin films of water to areas of lower stress, where it reprecipitates, filling cracks and bonding rock surfaces together. This process, called pressure solution, proceeds over thousands of years, gradually strengthening fault zones between earthquakes. The chemistry requires only pressure, a tiny amount of water, and time, transforming mechanical stress into chemical dissolution and reprecipitation. This slow cementation helps explain why some faults can lock for centuries, accumulating stress until the chemical bonds are overcome by tectonic forces. The patient chemistry of pressure solution works to heal the Earth's fractures, though on timescales that seem instantaneous only to geology. The slow oxidation of wine in a sealed bottle represents chemistry that can improve or degrade quality, depending on conditions. Even in a corked bottle, tiny amounts of oxygen slowly permeate through the cork or remain dissolved in the wine. This oxygen gradually reacts with phenolic compounds, tannins, and other molecules, changing the wine's flavor, color, and aroma over years or decades. In well-made wines with sufficient tannins and acidity, this slow oxidation can improve complexity and soften harsh flavors. In others, it leads to deterioration, producing flat, oxidized flavors. The chemistry proceeds slowly in the cool darkness of a cellar, each molecule of oxygen triggering a cascade of reactions that subtly reshape the wine's character. This transformation, neither fermentation nor spoilage, but something in between, demonstrates how slow oxidation can be desirable, a controlled chemical evolution that requires years to complete. The gradual dissolution of glass in groundwater, though extremely slow, eventually affects even this seemingly permanent material. Glass is thermodynamically unstable in contact with water, especially alkaline water, and will slowly dissolve over centuries or millennia. The reaction proceeds from the surface inward, as water molecules break silicate bonds and leach away sodium and other modifying elements. Ancient glass artifacts sometimes show iridescent weathering layers where this slow dissolution has altered the surface. Buried glass can develop a thick patina of weathering products, though the process requires thousands of years to become pronounced. This chemistry proceeds so slowly that glass is often considered permanent on human timescales. Yet, given enough time, even glass returns to solution, its molecules dispersing back into the water from which they were once gathered. The slow formation of natural magnets through the cooling and chemical alteration of iron-bearing minerals reveals chemistry's connection to Earth's magnetic field. When iron-rich minerals crystallize from magma or precipitate from solution, they can record the direction of Earth's magnetic field at the time of their formation. But chemical changes after formation can alter or erase this magnetic record. Oxidation, reduction, and mineral transformations proceed slowly over thousands to millions of years, sometimes destroying the original magnetic signature, sometimes creating new ones. This slow chemistry complicates the reading of Earth's magnetic history, but also provides information about the chemical conditions that rocks have experienced. The gradual alteration of magnetic minerals continues today in rocks around the world, quietly rewriting or preserving the magnetic memory of ancient times. And so we arrive at a place of rest, having wandered together through chemistry that never rushes. We have watched rust bloom on iron over years, observed caves grow drop by patient drop, and followed the slow transformation of life into stone and stone into soil. Each process unfolds in its own time, governed by the fundamental nature of atoms and molecules, by temperature and pressure, by the presence or absence of water and oxygen. These slow reactions remind us that not everything in nature happens in a flash. Some of the most important transformations require patience beyond human measure, chemistry that works steadily across decades, centuries, or millennia. The Earth itself is shaped by such reactions, landscapes carved not by sudden catastrophes, but by the accumulated effect of countless small chemical changes. There is something deeply comforting in this knowledge. The world is not only a place of rapid change and dramatic events. It is also a place where chemistry works quietly, where transformations unfold so gradually that they seem almost like stillness. Rock becomes soil, organic matter becomes fossil fuel, minerals dissolve and reprecipitate in endless patient cycles. You are safe here, in this moment, as chemistry continues its slow work all around you. Your own body participates in these gentle reactions, bones slowly remodeling, proteins gradually turning over, each process proceeding at its own measured pace. You are part of this patient world, connected to the same chemistry that forms caves and ages wine, that turns wood to stone and glass to crystal. If you are still awake, know that more stories await, more gentle explorations of the natural world and its quiet wonders. But if sleep is calling, you may rest easy, knowing that these slow reactions will continue without you, that the chemistry of the world proceeds whether we watch or not. There is no urgency here, no need to hurry or strain. The reactions we have explored will still be unfolding tomorrow, next year, 1,000 years from now. Let your breathing slow like the patient oxidation of iron, like the gradual formation of a stalactite, like the transformation of sediment into stone. These processes ask nothing of you. They simply continue, steady and sure, following laws that have governed matter since the beginning of time. The world is full of such patient chemistry, reactions that measure time not in seconds but in seasons, years, or ages. They remind us that endurance is built into the nature of matter itself, that persistence is not effort but simply the way things are. Molecules find each other across distances and time. Bonds form and break according to ancient patterns, and the great slow cycles continue. Rest now, if you wish. Let these images of slow chemistry accompany you into sleep. The gentle rust spreading across metal, the quiet drip of mineral-laden water in a cave, the gradual darkening of silver, the patient transformation of rock into soil. These are the lullabies of the earth itself, chemistry that whispers rather than shouts, that works in silence and in darkness, that asks nothing but time. Good night, gentle traveler through the realm of slow reactions. May your rest be as peaceful as a molecule settling into place, as calm as the patient work of water on stone, as deep as the quiet darkness where chemistry shapes the world grain by grain, moment by moment, through time beyond measure.